They just told me back there that apparently there's a golden rule in book publishing that says that with every formula you show, you lose half of your audience. And I have 2 on my first slide. But I only want to show you these formulas to illustrate that with just a few symbols like F equals M times A, we can describe a wealth of phenomena. From the earth, around the sun, from a ball game, from your bike ride, everything. Or if you're a communication person, you may like Maxwell's equation. Everything we do with our radio or mobile phone communication, or actually the fact that we see each other, is all described by this very simple Maxwell equation that you see here. It's so simple. It describes basically these 2 equations, describe basically everything in our daily life. But there's more. Besides our classical world, there's also a quantum mechanical world. And this is the world of atoms, molecules, the very small particles. And again, we have a very simple looking equation. It has a Greek symbol in it. That makes it a little bit obscure. But otherwise, it's fairly short. And please be impressed that this equation, the Schrödinger equation, describes all of chemistry. So in some sense, because our bodies are big chemical factories with all the atoms held together by quantum mechanical glue, our existence is thanks to quantum mechanics. But maybe with this third equation and losing another half of the audience, that many people think, well, these small particles, they're not my thing. Or formulas, I never have understood them. I'm more of the human scale. I want to feel things or hear things or maybe even touch things. In that case, you're the right person for me to talk to, because I will not show any more formulas in my presentation. I will actually show you some quantum objects that you can actually see, you can actually hear them, and you can touch them. So let's start. It all starts actually up to a few minutes ago before I came on stage, that quantum mechanics was describing very well and very accurate the world of atoms and molecules. But then at larger scale, and it already starts at our unit, the biological cell, it kind of stops. A biologist takes the cell as the fundamental unit to build up biology. This is an enormous simplification because it completely ignores quantum mechanics. But it is as best as we can do at this moment. Larger objects like our hair, which is basically the smallest thing we can see with our eyes, or us, that's all classical. But the small things can be described very accurately. And the people who put forward this theory, the quantum theory, are actually, maybe they've made the greatest intellectual revolution of mankind. You see a picture here with, on the first row, very prominent Albert Einstein. You clearly recognize him in the middle. On his right, left for us, there's Hendrik Lorentz, our Dutch hero. And next to Lorentz, we see Madame Curie. And many of these men in this picture have received a Nobel Prize for their great work. There's one person who got the Nobel Prize twice. And that's actually the only woman in the picture, Madame Curie. So apparently it's true what they say, that women have to perform twice as good in order to be part of the gang. She did it. So, this is 100 years ago. What's new? Well, present-day geniuses look like this. This is a group of brilliant people that form our group at the TU Delft. But again, they are at the verge of a new quantum era. We are no longer studying atoms and molecules as given by nature. In contrast to that, we actually design and make, by using very advanced fabrication techniques, new objects, much bigger, but that still show this absurd quantum mechanical behavior. So what is actually absurd about quantum mechanics? Why are we so excited about our quantum stuff? Let me give you 2 examples of absurd quantum mechanics. The first example is quantum superposition. Let's take a particle, like an electron or something, and bring it into a ring structure. The particle can take the upper arm to get to the exit, or take the lower arm to get to the exit. Now, what actually happens in quantum mechanics is that the electron takes both arms at the same time, simultaneously. Really, it's sitting in the upper arm as well as in the lower arm at the very same time. And we know this because we follow the particle and we see that at the exit of the ring, it actually collides with itself. It bounces into itself. And we observe this as interference. And such a superposition of being at two different locations at the same time has been very thoroughly checked in all kinds of experiments. Quantum superposition. The next example is the example of entanglement. And we start very simple. We take, let's say, a red particle and a white particle. Very classical colors. Then the next step is that we bring them together. And we make them interact a little bit. So we bring them very close together so they feel each other. And by virtue of this interaction, they become entangled. They take over each other's properties. So in terms of color, they become white-reddish. Now that's okay. The curious thing happens if we take them, we entangle them, and bring them apart. And while taking them apart, they remain entangled. The one that's on the left for you still has some properties of the other particle, which can be at a very large distance, as far as the size of the universe, in principle. So that's entanglement over a very long distance. Particles keep having each other's properties. So what can we do? How can we actually measure that? Well, the problem is that if we measure it, we have a classical, let's say, color measurement apparatus. And the color measurement apparatus is a classical thing, so it can only give classical answers. So it says, let's say, red or white. So if I say, well, particle on the left, what is actually your color? And I measure it. It says, for instance, red. But maybe you notice that the particle on the right, at the same moment, became white. And let's check it again. I measure the left particle, and the one on the right immediately becomes white. And that's because color is a conserved quantity in the universe. So if something completely turns red, there's something else where it used to be entangled with is completely turning white. And this action over a large distance, and remember, it can be the size of the universe, these particles can be apart, takes place instantaneous. Let me put it there. A measurement of the color on the left particle immediately changes also the color that's far away. And so if I do something here, and at the same time I change something there, without any signals traveling over to actually say, well, you just go there. There's nothing in between. Much faster than the speed of light. So this is a prediction from quantum theory. And one guy, Einstein, said, that must be wrong. Any theory that predicts spooky action on a distance, do something here, change something there, that's a prediction that tells that the theory is wrong. It doesn't say it's possible, it tells the theory is wrong. Luckily, we also have other heroes in physics, and this is a theoretical physicist called Richard Feynman. And he said, let's not be bothered with all these philosophical, consequences of our theory. Let's calculate and see what happens. Now here at the Delft University of Technology, we educate engineers, actually guys like me. And our approach is that we feel challenged. We say, okay, let's do it. So what do? We take these two particles, we bring them far apart, and we make it a bit more complicated. We bring in a third particle, a green one. The green one we bring to the left one, and we make these two interact. I'm going to give them some interaction, but view the graph carefully. You see that at the same moment, when these two interact and share some color, also the particle on the right, which was still entangled with the first one, also becomes green a little bit. Now next is that I ask for color. Hey, left particles, I do a color measurement. And they, for instance, turn white-reddish. At the same time, the one on the right becomes green. So look what I've done effectively. Let's start again. I bring in the green particle, they entangle. They're also entangled with the one on the right. And I click once more, and the one on the right is now green. I have teleported the green particle from the left universe to the right universe over a long distance, instantaneously. So this teleportation is what we call, let's say, absurd or strange or very odd. But we can do it, and we actually do it. And actually, we do this in the lab, and we've actually done it so many times that we actually made a student-proof setup. Now, I can tell you, if a setup is student-proof, then it's a very robust setup. All right, so what do we make? We want to make some stuff that we can actually use and do something with. First of all, a very simple example of a light bulb. It's a plain wire. If we send a current through the wire or if you excite it by light, it also luminesces a little bit of its light. But in this case, the wire is very small. It's only nanometers in diameter, maybe a micrometer long. Now, at the red arrow that you see, we excite the system with some laser light, and we actually look what comes out of the wire. And if we do that, you actually see a little bit of there was a little bit of light coming out of it, the thing, right? That bright spot. Now, what is special about this bright spot, that if you analyze it with a good detector, it actually comes out as a stream of individual light particles, one by one. It's no longer a stream of light, it's really granular. One comes out, the next come out, etc. And these are our photons that we use in these color experiments to teleport. Let me give you another example. Different type of, if you're more the hearing person, then let me take a string. And with all our strings, guitar or violin or whatever, if you put a little tension on the string, the tone of the music goes up in frequency. The tone goes up. So we've taken a very thin wire, a nanotube, only 1 nanometer in diameter. We suspend it over a trench. We clamp it very tightly at 2 contacts. And we excite the nanotube with an electric pulse. It starts to vibrate, and we hear the tone. Now, what is special about this particular vibration is that it's very small, so it's also very sensitive. So if we add 1 electron, 1 quantization of electrical charge to this nanotube, there's a little bit of extra tension into the nanotube that changes the tone a little bit. Let me hear you the sound of electrons. The composition could be a bit more interesting, but the change in tone, if you go from one level to the next level, that change is induced by 1 particular individual electron. You hear, let me let it hear again, what you hear are individual quantum electrons. It's coming to our lives, and they become audible. Now let me give you the most recent example that comes straight from the lab of my colleague Leonardo Di Carlo. And actually, I need to do something for this. Because we have, the Di Carlo lab actually made a box. You see the box already on the picture on the upper right, with a few coaxial connectors to it. And if I get my gloves on, you will actually let me touch the box. All right. And the box is big. I can hold it in my hands. And what we do in our group is to make small electronic elements. Elements that are so small that they can process information in a completely different way. Instead of having bits of 0 and 1s, we want to make superpositions of bits. A superposition of being 0 and 1 at the very same time. But we want to make them on an electronic circuit. And what Leo Di Carlo has done is make 3 qubits. And I'm going to zoom in a little bit in a few seconds, but you already see the box with 3 qubits in it. And these 3 qubits, they can be put in a superposition or be entangled together in any arbitrary way that we wish. Now, let me see if the camera can actually show you the qubits. There must be more zoom. So this is my finger. So this is the size of the system. And I hope you can see that there are 3 black spots on this quartz plate. And these 3 black spots are about 1 centimeter away from each other. And these are our qubits. the qubits which are in a quantum superposition, and we can entangle different qubits together. Yeah? So we're now on a chip of centimeter size. So the distance between the different qubits is about a centimeter, and we can perform all this quantum absurdness on this chip at a visible length scale. All right, so you've seen it. Now, of course, it only works if the details are fabricated very, precisely, and the details are nanometer scale. And so it's not just that every centimeter object starts to behave quantum mechanical. No, you really have to engineer it very precise up down to the nanometer scale. That's the picture that you see right here. Okay, let me zoom out a little bit. What are we trying to do here? Well, we actually want to make quantum mechanical systems and use the richness of quantum systems, like the extra possibilities of being in superpositions and having very fast teleportation over long distances, also in technology. Can we make applications that are much more efficient than we have today? And particularly, because we're in the quantum information business, we want to extend the quantum, the level of quantum from the atom to a transistor. That is already the case. That's working very well. But we want to bring it even up to a higher level of complexity, that a complete electronic circuit behaves quantum mechanical. And it would win so much in efficiency, you would not believe it. And that would also make our gadgets a lot faster. Now, only a few years ago, people also in our field were saying that that's not going to happen. That's inherently impossible with quantum mechanics, to bring them up to a larger scale of size and complexity. But with the progress of the last few years, I can really say here, actually I'm saying it for the first time in public, this clear that it will come. Yes, we will be able to make quantum circuits, and a quantum computer will only take maybe a decade later or so. All right, let me conclude here with a take-home message. I started with some equations, including one for quantum mechanics. But there's one message, that up to a couple of minutes ago, quantum was only restricted to the small objects, but from now on, it has arrived to the human scale. And we can see it, we can hear it, and we can touch it. Thank you very much, and have a great day.